formal definition of the limit as x approaches a of a function f of x being equal to L is saying that for every distance epsilon around L on the y-axis, there's going to be a distance delta around A on the x-axis such that whenever x lives in the open interval of x's from A minus delta distance to A plus delta distance, then you can trace its y partner living on the y-axis between, so that's f of x, living between the limit L minus the distance epsilon to L plus the distance epsilon. Okay, so this should happen for any delta that I choose. Okay, so when I choose a delta, I should be able to say this is the interval around the x equals a value that makes sure that every x value living in that interval is going to have a y partner living in that interval of epsilon around the L value. Okay, so try to digest that while we go to the next example. The definition of the limit as x approaches a of f of x equals L shows that we can prove that a limit exists by choosing an appropriate distance delta. Okay, that's a positive number because distances are positive, and this distance delta is going to be centered on the x-axis at x equals a. And if we can show that by choosing this appropriate value that all y partners to the x's in this x interval live within a y interval centered at L, then we prove that this limit is equal to L. Okay, so in this type of example, to help you get a good idea of what's going on here, digesting this definition, we're given this graph. And in this graph, we have L equals 6, and we drew this function f. And around L equals 6 on the y-axis, we've drawn an open interval from 4 to positive 8. So there's a distance of 2 above and below L equals 6. That means that our epsilon distance above and below L equals 6 is 2 in this particular example. If you look at the x-axis, we have A equals 4 on the bottom, on the x-axis, and then we see that when x is equal to 3, we have the y partner 4, okay, and then when x is equal to 7, it has a y partner 8. The problem is that this is not a symmetric interval on the x-axis centered at A equals 4. So what we're going to do is we're going to come up with the value delta, the distance from to the left of A equals 4 and to the right of A equals 4 on the x-axis that will have us give us a nice symmetric interval around 4 where all the values in that interval will map back to the y partners in the interval on the y-axis anywhere between 4 and 8. So specifically they ask us to find some positive distance delta such that the absolute value of x minus a is smaller than the delta that we find, would imply that the absolute value of f of x minus L is smaller than the epsilon. Okay, what does it mean to say these absolute values of these differences is smaller than a number? Well, another way of stating this would be to say that the x is in the open interval from a minus delta to a plus delta, implies that the y partner f of x is in the open interval from L minus epsilon to L plus epsilon. That's exactly what those absolute values are saying. Okay, so let's find this delta. Here we have A equal 4, L equals 6, and epsilon equal 2 in this particular limit. We don't know what the function is, so we're working with the graph. To make the interval around A, the x value A, which is equal to 4, symmetric, we consider that all the x's in the open interval from 3 to 7 have y partners f of x that live in the y interval from 4 to 8 on the graph. Now I got that just by looking at the picture, all right? All right, but we want to make this thing symmetric. So to make the interval symmetric on the x-axis, we are going to choose a distance delta on the x-axis that's the smallest of the distance either to the left or to the right of a equal 4. So look at a equal 4. We're contained within 3 and 7 with this picture of this particular function. So we're going to say, let's let delta equal the minimum of the distance on the left to the edge, which would be 4 minus 3, that's 1 unit, and the right side, which is 7 minus 4. So we're looking for the minimum between 1 and 3. The minimum between those two numbers is 1. That's the smallest. Now check that this does what this does to your graph. Well, when we restrict ourselves to x values that are between 1 and 3, in other words, that are restricted to 1 unit to the left and 1 unit to the right of the center 4, we get the interval from 3 to 5. Okay, and all the x values that live on that x interval between 3 and 5, that's 1 unit to the left, 1 unit to the right of a equals 4, all those values in that symmetric interval, they partner with y values that live within the y interval of 4 to 8. So we found a good choice for our delta. Okay, well, that's how you would handle it if you were given a picture. But what if you were given a function f of x? Well, to do an algebraic proof that the limit as x approaches a of f of x is equal to L, they're going to give you numbers and values for this. The first thing you do is determine what the given values are. In other words, what a value is x approaching? What is the actual function that we're working with here? And what is the limit that it equals? L. Then you're going to do some algebra to relate the absolute value of this f of x minus this L to the absolute value of x minus a. And once you've established this relationship, you're going to use that step to find an expression for delta that will make that absolute value of your f of x minus L less than epsilon. Okay? So you're going to come up with a value for delta that's going to make your absolute value of f of x minus L smaller than epsilon. And once you've done that, you've got everything you need to do the formal proof. And you do that by making an assumption that the absolute value of x minus your a is smaller than delta, and you're going to let delta equal the expression that you acquired in the previous step, and then you're going to show that the absolute value of f of x minus L is less than epsilon. That's the outline for every one of these proofs that we're going to see.